Yeah, so as I said, 1 year ago we came to Ray Summit to learn how we could be using this technology to help scale our solutions at Touch Medical Intelligence. Today I'm actually very proud to be here to explain and introduce how we're using Ray to what we think is transform the technology of health. So this talk is going to be broken down into 4 parts. So the first one is basically some philosophy of stateful and stateless services. We'll then talk about the use case at Touch and how we're using that. And then I'll introduce something called StickRay, which is this technology we built on top of Ray to make this possible. And then the technical details, which I think if you made it this far, this is probably the most interesting thing. So a little bit about me. I'm founder of Touch Medical Intelligence, and I'm an astrophysicist at Caltech and Leiden University. This is me on the internet, what I look like, and when I had shorter hair, at least. And you can find me on these social media platforms like that. So I'm going to start off by saying that despite the revolution of large language models, the real breakthrough with AI is its ability to create highly personalized experiences. And actually, I just saw this article today pop up from yesterday where one of the founders of DeepMind is talking about how the real value in today's climate is the interactive component of AI and how our large language model kind of stuff is going to be eclipsed by that in the very, very short-term future. So it's just kind of coincidental, and I think it was a good sign. So I'm going to start very quickly just with a history of distributed computing and where we've come from. The main idea is that we started off with computers in the 60s, and the main idea was that we thought that they were only good at communicating. They weren't really good at anything else because they were just too slow. But then we started to realize that actually they can do more, they can compute things, and we came up with large local area networks. We're all familiar because we're probably partially gamers here. We had our LAN parties. And then in the 2000s came companies like Amazon, Netflix, microservices, and then we eventually arrived at the stateless kind of revolution, and then even now serverless, where you don't even know, the developers don't even know about the server, and all they care about is the actual cost of running their server in the cloud. And the main thing about this is that it would never have been possible, even if we had the knowledge now to do AI, to do it in the past, because we just didn't have the scale. So not really any new news to anyone here. So just to come into like kind of the stateless and what it's like. So we have some clients. In a single node setup, we have a server and a service. We have a database. And eventually, at some point, your user base grows, and you have too many clients for the one server to handle. So you horizontally scale out the servers, and now those clients can easily be handled by you and your product. They're all, at this point, still talking to the same database, and eventually we come up with things to solve that by coming up with like distributed databases and things like that. We call this the data shipping paradigm. And what we're saying with that is that we're sending all the information necessary to carry out the request with the data packet, with the request packet itself. And so your request comes in from the client, it gets round robin to some server, it gets handled, and the next time when it comes in again, it's going to get round robin to a different server. And in both cases, what you're doing is you're retrieving data from the database to make that thing possible, and then it just disappears. The data just disappears from the server. So it's kind of a little bit wasteful. But what we like about it is that it's super simple. We trade off that wastefulness for simplicity, and that's always a good thing. So let's talk about the stateful counterpart. We have stateful services. And the thing about them is what's called data locality and available consistency. Data locality referencing the fact that we're going to be leaving state on the server. Available consistency, coming back, if anyone remembers that CAP theorem, the triangle, maybe like your partition, your availability, and consistency. We can only ever have availability or consistency because we always have P. We always choose availability because we want to have good products. So stateful services, we call them availably consistent because we still choose that availability, but actually we get a lot of consistency out of the box with them. So that's what they're good for. So we actually call this the function shipping paradigm because we're actually shipping a directive to be handled by your server. And in this case, when after the first request is handled, we're going to stick that data that we pulled locally in, and the following requests will be handled by the same server, and so the data stays on device. That's the data locality. So we do this with a lot of different technologies, but the main ones being sticky connections and persistent sessions. And the main principle is that we're going to always be routing the same user's request to the same server. And one way to think about this is basically that stickiness helps the client reason about what's going on the server side. And there's this really cool blog post by Werner Vogels, CTO of Amazon, where he talks about eventual consistency. And the thing that actually matters is that when you have user requests coming in sequentially, the time that really matters is the time between page reloads. And if you have consistency between those events, that's eventual consistency, and that's actually what matters. And that becomes very relevant to anyone who's doing anything with stateful services. So in today's climate of kind of growing personalized experiences, sticky connections should be top of mind. They are definitely making a comeback, and they've been doing so for numerous years now. And Ray dominating the distributed landscape is basically a perfect candidate to have them. So it's a bit strange that we don't have them. We have Ray Serve, that's stateless, and it's wonderful, but we don't have sticky connections for serving. So wouldn't it be nice if we had that? But first, last little kind of philosophical digression. I've had lots of discussions with people who, what I would call like kind of the stateless always, having the stateless always mindset. What that means is like there's this tendency to prefer that statelessness because it is so easy. And while that's nice, it's actually really important not to forget that you need to be making informed decisions when you're designing systems. So being a physicist, I always come back to axioms, and so one of them being kind of the principle of least action, or the path of least resistance, basically saying that if you deviate from that path, then we consider that a design flaw in whatever discussion you're having. This kind of concept exists in many fields of thought, from physics, circuit design, systems design, even philosophy. So when you do that, you're actually going to get a number of very cool benefits from that, from simplicity, efficiency. If you're working with a team, it becomes very easy to collaborate with that team. And basically what it allows you to do is focus on the value at hand. So really focusing on the value because you're kind of circumventing those kind of rabbit hole discussions. Not to say they don't exist even when you follow this principle. So yeah, I've had many of these discussions, and I've summarized kind of all that in this helpful like kind of diagram to help people, systems architects, if they ever do need to make that decision. And yeah, I encourage you to screenshot this because we'll be, especially for you folks at home, and go through this at your own leisure. But basically what it comes down to is looking at what's the primary objective of the thing that you're building. If it's user experience, and you're going to be building features where that consistency between requests is very important, then there's a good chance that you'll want to consider stateful. If, on the other hand, scalability is top of mind, which it is for pretty much everyone here, you still need to ask yourself, do you care about consistency? And that personalized experience usually depends upon consistency. And if you need to do several workarounds to make that possible, well, that increase in complexity actually is a good reason to consider scalable, stateful solutions. And that's why what we've built we think is kind of interesting because it allows you to do that with Ray. So some common use cases would be like multiplayer games, banking, navigation, and actually what's really interesting and like kind of applicable right now are these personal AI assistants. So if you use Siri ever, the amount of state that requires to handle your kind of interaction is huge, and it's a stateful service, along with numerous other ones. So that's all great in theory, but I'm very proud to kind of talk about our use case at Curate Health, which is using these stateful connections. So Curate Health will transform how we understand ourselves. We're now able to predict the near-term future and understand what will happen to our health. So let's talk about what that means. So basically, on the one side, we have data coming in, and the data is being collected from a user by some AI health assistant. On the other side, we're generating predictions of the future. And in this talk, I'm going to focus on the left-hand side, the generation of data, the collecting it from the user part, and we'll show how that's a really personalized flow. So coming to kind of an overview of that, so when you log in, your health assistant is going to think about what it needs to ask from you, what it needs to know from you at the moment. It's going to ask you that. You're going to respond. And depending on what you say, your health assistant might decide that it needs to change topic. It might need to totally reevaluate how it's collecting data from you right now in the moment. And it's going to keep doing this until it decides to stop. So taking a look at this simple kind of code snippet that kind of describes that. So you're logging in. Your user data is pulled. An assistant is spun up. And then we're going to enter this process of decide, act, and update. And then eventually it's going to stop. And it depends on the user's data. Now, if in each of these scenarios we had to pull in the data from a database and to spin up an assistant just to handle a single request, we would not be able to handle any requests because we would not be scalable. So from a high level, it kind of looks like this. So we have the client, we have the database, we're pulling it in, we're using sticky connections. And what I want to call out is that sticky connection and statefulness is actually really symbiotic with stateless subsystems. And so behind the scenes, we're using stateless actors all over the place to do their job because stateless is great and it is simple. And sticky and stateless play well together. So that is a key thing here. So, and kind of one of our driving factors in our design considerations, which we'll talk about. So that, just in a nutshell, just to recapitulate what we're doing, we're running game-like scenarios with users because we need to collect that data in a very engaging, interactive way. Interactive AI, again, being super paramount to the future. We're using language modeling, LLMs, to interpret the user's responses, to respond back to them, and extract information from those responses. We're using real-time analytics to actually figure out what is going to be the most, well, first of all, the predictions, and we want to reward the user for their data. And then we're doing content ranking and delivery in real time. So how are we doing this? Well, we built something called StickRay. The name kind of says it all. And I'd like to introduce that to you. So what is StickRay? StickRay is a scalable, resilient, sticky connection library built on top of Ray. We wanted it to be as scalable as Ray serve and resilient to failures, and resilient also to load-based attacks. Load-based attacks are your DOS-like attacks, and I'll just call out that stateful connections are particularly exposed to those types of attacks. We want it to be robust to that. It's well-tested, or it will become more well-tested as the community grows, because it's open source, and we want this to be used. You can use this for whatever you want. So I'd like to take you through some of the design considerations, because as I said, you trade off the simplicity of that you get from stateless for the consistency and the data locality. So that means that the developer's job is a lot harder. I mean, the developer at StickRay. Our job becomes a lot harder to make this thing work. So we need horizontal scalability of workers, things that are actually handling and managing those sessions. We need scalability, horizontal scalability of the routing, because we can't have bottlenecks on routing those requests. We need to avoid transferring sessions between workers. And this is actually super important because when you're handling highly personalized flows with AI or anything, you're using often various types of primitives that can't be serialized, like locks. So we have things that can't be transferred all the time. Resilience, as I said, we want it to be simple and we want to play well with Ray serve. Because, we want this thing to be symbiotic with the rest of Ray. So you can see in this code snippet that actually the StickRay kind of API and implementation resembles Ray serve quite a lot, the serve deployment thing. And in fact, it's supposed to, on purpose so that it's easy to kind of read your code when you're using this. So you just kind of decorate a class, you implement some methods, and you have a stateful service. And those methods that you can create, this is actually where we start to deviate from Ray serve and introduce things that allow us to build highly customizable workers. So going back to our example at Touch, we have the create session worker. And so when we create our session, what we're doing is we're pulling in the user's data and we're spinning up an assistant. So we do that. Then we use it, but eventually we need to close that down. We need to close the session, so we have a closed session method that you can implement, so you can tear down that assistant. You can do anything you want, store, state, checkpoint, stuff like that. We have an initialize worker entry method as well, which allows you to make database connections that maybe you need to maintain over the course of this. And you have a shutdown method, which allows you to tear those things down as well. And so it looks, you could see kind of like a very minimal plain Jane implementation might look like this piece of code here. So you can implement these, like just these methods. And they're all optional. You don't have to do any of them. So, and if you don't implement any of them, you get a stateless service. That's kind of cool. So here's a toy example. It's like the hello world of stateful services. So it's basically, we're going to say hello world name, and the world name is just going to be your session. And then we're going to tell you how many times you've interacted, which sounds super simple, and it is super simple because it is simple. The difference here is that we're going to create a session. We're going to store that the count is 0. We're going to store the session ID, and then we're going to implement a function called say hello. And in red, we've highlighted session ID, which is a keyword-only parameter in this kind of say hello function. And this is how you expose your method to the routing layer. And it's really, you just need this keyword-only session ID in the function, and it becomes exposed. You can use it from outside in the outside world. So when you run this, to run this, you need to deploy it first. It looks a lot like RayServe. It's one line of code. Then you need to get a handle. That's also one line of code, very easy. And then you can use this as you would use anything else in Ray. The difference being is that you don't have to use a .remote. We found that really annoying, so you don't have to use .remote. You can just put your things right into the method. I don't know if anyone else finds the .remote thing annoying. Yeah, and I'll mention that sessions expire. So we have like, if we wait for over the expiry time, we're going to reset that session. And what that means is that in StickRay, we're going to like tear it down, and we're going to create a new one if you send in a new request later. So this is the toy example. Again, it's as simple as that. So now we come to the kind of the cool part, the technical details, and how StickRay works. And so as I mentioned, we've already talked about like workers and sessions. I'll just quickly recap. A worker is an actor, and it manages some sessions. Sessions are those things that are specific to that session, the user or whomever whatever you're handling. It gets its own session. And we build in session isolation so they can't interact with each other. It's built in by the API. And workers automatically scale out horizontally just by the nature of them. Ray gives us that for free. On the routing layer, which we haven't talked about, we get something that looks like this. So each node gets its own router. And those routers are all able to correctly resolve where a session needs to go. The main thing about the routers is that they're all independent, and they're all using eventual consistency to work independently and stay up to date. And we're going to talk about what that is. So in this case, you can see that like a session could come into either node, and it's going to figure out where to send it. It's going to do that really quickly and easily. So deployment layout looks a lot like this. We have a controller, which is very similar to RayServe. We have, which is going to manage auto-scaling, service management, and has also a consensus ledger. This is different from RayServe because we need some extra little kind of pieces to make this thing work. We also have something called an event bus, which is just how we allow workers to communicate with routers or whoever wants to listen to the worker, and it's done in a kind of pub/sub manner. And now we come to the heart of this, what makes this a challenging thing to build. It's the horizontal routing problem. Because again, those routers are all independent, and they don't talk to each other. So how do they stay up to date and consistent? So it comes down to this confusion matrix. We've all seen them before in machine learning or in other realms. We have reality, where a session either exists or it doesn't exist. And then we have what the router thinks. Now, the router might think that the session exists or it doesn't exist. And ideally, in the ideal world, we want those two things to line up. We want them to be consistent with each other. But unfortunately, in the real world, that doesn't happen because they're all independent and they're all working independently. So we can think about this in terms of probability. And what's the probability that my router doesn't know about a session that actually exists? And you can work it out. It's fairly easy that it goes as 1 minus 1 over n, the number of routers. And you can see that as the number of routers grows, the probability that the routers don't know about something that actually exists will just tend towards 1. It's going to basically mean that you're always inconsistent as the number of nodes grows. And that's not good. So basically, a successful routing in a stateful setup looks a lot like magic cups. It's making a good guess about where the session is. And there are a number of well-known options. This is a well-studied thing since the 60s. Again, two sides of the same coin, stateless and stateful. We've been doing them for decades. But we're going to talk about distributed hash tables, which is probably the coolest, or the most complicated as well. So there's a few ingredients to making this work. The first one's called gossiping. So in gossiping, you have basically a periodic broadcast from every worker to the event bus. And whoever cares about those broadcasts are going to read those broadcasts. And this gossiping happens on a time interval of, let's call it capital T. And then you have your two main events that can happen in a stateful setup. You can have a new session being created, or you can have a session created already and sending in requests to use the session. And those two things have two characteristic timescales of happening. So session creation is like when a user logs in for the first time. That happens rarely. It's very slow because there's only one user, only so much time in their day. They can't do two things at the same time. So it's a kind of a slow process. On the other hand, the requests that follow that creation are quite rapid and happen frequently. And they can happen almost simultaneously. So there's these three kind of components to the system. And what I'll kind of posit and just say is that the rate of requests is much smaller than the rate of new sessions being created. So when you kind of work that into your math and you figure it out, you find out that there's this, the probability that that router doesn't know about the session gets a new factor. So where it was 1 minus 1 over n before, you get this new factor here that depends only on two things. One is that time scale of gossiping, and one is the time scale of new sessions being created, which again could just be once a day. Maybe your user logs in once a day. Actually, we can tune that gossip parameter to make that thing really small. And in fact, that's what we do in StickRay. So it's one of the tuning parameters that adaptively gets kind of figured out, and we do that by measuring the rate of new sessions. And when we choose it well, that probability just shrinks down to 0. The other thing that's important is how we choose where to put the session. And we use something called quasi-consistent hashing. Any CS people here will probably know about consistent hashing. But it's kind of simple, but also kind of weird. So you have a session ID and you have a node ID. And what you're going to do is hash those two things down into an integer. And you're going to put them onto this kind of looping ring of integers. You're going to figure out where they go. And in normal consistent hashing, you just assign you assign a session to the closest worker on the ring. And that's all the small blue balls go to the big blue ball, the small green balls go to the big green balls, and so on. And that works really well when the number of workers stays the same. But when workers come and go, you have to reassign those sessions to other workers. And as I said before, we can't reassign sessions because some sessions can't be serialized. So we have to take into account that, and we have also hot nodes. So hot nodes are another situation where nodes can become unavailable, they're under load, and so we have to do something about that. So quasi-consistent hashing is a way to just take that into account. We just skip the hot nodes, or we skip the ones that are not there. And you lose that determinate kind of promise from consistent hashing, but that's okay, because we're going to resolve that in the next step. What it gives you, though, is a better guess. Again, coming back to that making a good guess of where the session is, you're playing a game of magic cups, so it gives you a better guess. So in the situation where the router guesses wrongly, and again, we want the chances of that happening to be really small, but sometimes it's going to happen. When it happens, you need to do something about that information. So we stake a claim. And that means that the router is going to talk to the controller, and it's going to get consensus on where that session is or where it should be. And this is a strong promise. It can't be broken. And so the controller is maintaining that, and that's actually a bottleneck, right? If you think about it in a distributed system, having to talk to one guy or person or thing or entity who knows about stuff, that's a bottleneck. And so we want to kind of avoid that as much as possible. That's why getting that probability low is important. So bringing this all together, coming a long way. When a kind of a request comes in for a new session, we're going to check the router's local map. If it doesn't know about it, then it has to make a guess. And what that guess is going to use is first quasi-consistent hashing, and it's going to make that guess. And if it's right, it's fine, all's well. But when it's wrong, it's going to have to stake a claim. And once it knows about the session, we ferry that method along, and eventually we're going to gossip that out to all the routers. And so that, in a nutshell, is how stick array works. So I encourage people to join the discussion, the examples. It's rough. I said will be well tested. It's rough because we just put it out for this conference. And we're excited to get more people to kind of join the discussion and to find out its limits, really. So in a summary, at Touch, we are building a health experience, very personalized health experience where stateful services is paramount. And we've built a library on Ray for sticky connections called StickRay. It's like RayServe, but sticky, and it's open source. Thank you. Yeah, questions? Ooh. Does everyone know what gossiping and consistent hashing is? Probably. All right. Thanks.